let's get started on the practical part of this event. And so you heard about ASR and how it is based on ASE and Gpaw right now. We are going to do some exercises, and so ideally everybody would be sitting at their computer and working on these exercises, but the world isn't ideal. So now we have Corona, and we are doing things remotely, and everybody is sitting with their own computer. So this makes it a bit difficult to install all the software. So instead of doing it interactively, I will basically go through some exercises and show how to do things. And since ASR is so closely related to ASE and Gpaw, the first part here will be an introduction to ASE and Gpaw. And the second part will be about actually using ASR. And since this event also has a part which follows in a number of days, we will go all the way and try to demonstrate how to go towards high throughput. But today we will take it slowly and just and see how far we can get by hand, so to speak. So let's see. I'm going to share the screen, and so everybody can see the screen, I hope. And so if we go to the ASE webpage, we will find quite an abundance of documentation and exercises. And so the ASE webpage is located at wiki.physik.edu.dk/ASE, but some kind of routing issue, possibly with Eduroam, decided that this was not to be on my computer. So I have the documentation locally instead, but you can go to the ASE website and find all these things. And there is this getting started section, which is very good for, it has a lot of very basic demonstration of how to use ASE. And let's get started looking at those. So in ASE is a library for working with atoms. It means it contains tools to set up and run computations. And ASE doesn't really do the numerical part of the computations normally. Rather, ASE relies on a number of calculators, which are typically interfaces to external codes. So in ASE, there is this central object called atoms. And it represents a physical system with some collection of atoms in it. And then we equip that with a calculator, and we can do calculations. Also, we can write to different formats and visualize things. Let's try it in a terminal. So what we can do now, ASE is a Python library. So everything that we do in ASE, unless otherwise noted, is a Python script. So we can create an atoms object by importing it from ASE. And then we can tell it we want an N2, because we are following this exercise, and it wants us to calculate a binding curve where we drag a nitrogen atom and calculate the energy as a function of interatomic spacing. So we create an atoms object like this, and then we can run it and see that it runs. Now, the positions, we have specified that there are 2 nitrogen atoms, and then we need to tell it where they are. Right now, they are located at 0. I just printed the positions, and they are 0. So if we say atoms.positions index 1, comma 2 equals 0.5, then we have moved them a little bit apart. Now the first atom is located at 0 and the second atom is located at 0.5. And so let's calculate this binding curve. This demonstrates the power of ASE, that you can do any kind of calculation using Python scripts. So we need to write a for loop where we displace the atoms. And then we want to calculate the energy. So to calculate the energy, we import a calculator, and I'm going to demonstrate Gpaw here. So we need to create our calculator, and let's set some quick and dirty parameters. So we say mode equals LCIO. This means that it will use a cheap expansion in terms of atomic orbitals, which is quite fast for molecules. And let's tell it to use a standard, reasonably good basis of atomic orbitals with that. And then we need to equip our atoms with the calculator, and then we can get the potential energy, and this will trigger a self-consistent calculations. Now, instead of running all of this, I would like to just run a single calculation to check that it works. Now, I forgot to put it inside a simulation cell, so I need to do that. Atoms dot. We can center the atoms and give it a bit of space. Let's give it 4 angstroms worth of space. Now we should be able to run this calculation. And we can see that Gpaw spits out a lot of text. So is everybody more or less following? Is the video and everything working correctly? Also, should I be aware of any messages? Somebody's unable to view my screen. I would.
The screen is quite is tiny, so one cannot see what. No, I cannot say your screen is what your code you are on is quite tiny. It's not legible. Right.
Okay, I'm sorry for that.
So
which would be nice to know immediately. So let's try to change mode.
Yes, yes.
So this is a quite let's see, how does this work? It's called. Okay, does this work? Can you see my screen?
A little increase it a little if you can. You know, because if you still increase it.
Sorry, is everything good?
No.
Yes,
good.
so everything was increased. Was that okay? Good, thank you. And please, I mean, speak and say if there is anything which is not quite the way it should be. Now you should be able to view the basic windows, right, where things are happening, and see the text. Okay, I hope so. Thank you. Excellent. So let's again write our loop where we displace the atoms interactively. And now we can write the entire calculation. and it calculates. So there is one more thing that I would like to do. I would like to write each of these geometries to a file. So we use ASE's trajectory format. And then we write the atoms. After we calculate the energy, we write the atoms and any calculated quantities. So now we run it, and we should be able to see, aside from the text appearing, that also there is this trajectory file being written. We can see that it increases in size. So something is being written every step. So the energy right now is about -14, and then we are moving the atom out. And now the energy is increasing a little bit. So ASE, aside from being from the scripting interface, also contains a lot of command line tools. There is this ASE command with a lot of subcommands. Now, I'm not going to introduce all of those, but one that comes in handy is the GUI. So we run ASE GUI on our trajectory file, and we can see what it's doing. It opens several windows, one of which shows our actual system. We can see here the two atoms that we have, and we can go back to the first image because we are writing a long trajectory where they're displaced differently, and they were placed very close to each other. Then as we read the other entries in the file, we can see how we moved it apart, 0.1 angstrom at a time, I think it was. We can also see here it has plotted the energy as a function of the index inside this file. So every geometry has a number, and we can see this energy as a function of displacement. Now there are a few handy tools which allow us to plot graphs, and we can ask for the help and see that there is one which will actually give us the distance between two atoms and allow that to be used in a plot. So if we try to write D 0,1, the distance between atom number 0 and atom number 1, and we press enter, then we actually get the binding curve. We can see we started here rather close, and then as they move apart, the energy approaches a certain minimum. Now, the energy reference is taken to be the last image here. So this is not the true binding energy. To get the true binding energy, we would have to calculate the, we would have to subtract the reference from the isolated atom, and then we would get, I think it's -14 electron volts. Now time is passing, so let's not do that just now. You have seen how we can write scripts to do whatever we want. This is kind of this is the convenience of ASE. If you bother to go all the way and learn Python, then you can get it to generate all these calculations, and it will basically take care of what would otherwise be a long and tedious session generating input files for your favorite GFT code. Now, this example used Gpaw. Let's do a slightly simpler example as well to show another. So to show another standard task, namely structure optimization, and how one would do that in Gpaw. So let us say that we are interested in water, and as before, we can create an atoms object by telling it okay, so in this case we have an oxygen and we want 2 hydrogen. We are going to calculate the structure, so we pretend that we don't know exactly what it is. So we manually give it some positions. So let's assume that that oxygen is located at 0, and then we place 1 hydrogen a little bit away in one direction and the other hydrogen a little bit away in another direction. And then we do as in the last case. We create our calculator and equip the atoms with the calculator. And we also set our easy and simple parameters here, so it will be relatively fast. And let's redirect the output to a file this time, so it doesn't flood our screen. Now, if we want to run a structure optimization with ASE, ASE already has several implementations of optimizers that we can use. You have to import them. We can import the BFGS algorithm, a standard algorithm for atomistic optimizations. And then we can create an optimizer, and we create the optimizer around the atoms, and we can tell it to write a trajectory this time as well. So let's call it opt. And again, I have to remember to center the atoms inside a computational cell so that the computational code knows what kind of computational box to allocate. Now we can actually run the calculation. So we ask the optimizer to run until the maximum force is no greater than 0.01 eV per angstrom. And we can see it is running. And then we can plot again in the ASE GUI. We can see that the energy fell off like it should. And we can watch a little movie of what we did. If we select all 3 atoms at the same time, it will actually tell us the angles between them. So we can see if we go back to the first image, when we set it up, it had an angle of 90 degrees. And when we were done optimizing, it was close to, it was 103.2 degrees. I don't know exactly what the value should be with LDA. This is an LDA calculation. So this way we can perform structure optimizations. Now, ASE, one of the big strengths is that there are interfaces to many different computational codes. So let us say that we wanted to do the same thing, but not using Gpaw, rather using another code. So I happen to have CP2K installed, another computational code. And this one we import like this. And then instead of Gpaw, we create a CP2K calculator. Now, I actually have no clue how CP2K works. So we just run it again. I didn't give it any parameters here, so it's just running with the standard parameters. But we can see that it successfully did something. So the forces were a bit different and the energy reference is a bit different. So the optimizer log tells us, but it is basically optimizing. So this one was only a few iterations out. If we have a look at the trajectory, we should be able to see once again how the angle, this one is closer to 105 degrees. So Can everybody follow? So there are a few questions, so let's get to those. So Golapalli asks how to install Gpaw. And so Gpaw is available on PyPy. If you go to the Gpaw webpage, then there will be installation instructions, and the standard way to install Gpaw is to install it from PyPy, the Python package index. That is normally the recommended way. So if I can ask pip okay, so Gpaw is installed right now, so let's uninstall it. Now, if we say pip install, and then I don't want to install it system-wide, I just wanted to install it for this user. And apparently it finds that I have installed Gpaw already at the system level. So it did not actually, it says that Gpaw was already installed. So this is a bit annoying. I cannot show how it would look if you installed it as normal. But basically it tends to work pretty well. On a supercomputer, it tends to be a little bit more complex because you need to care about how to set up the libraries. So in Gpaw, this is the source code of Gpaw. You would generally obtain the source code, and then there is a file called siteconfig, and that one is a kind of template file which you can modify, and it has some settings that so if you want to link custom libraries, you would enable some of these if statements, and you would set the path, and then it compiles with that. It's a slightly non-standard code because it's written in Python. It's also available, by the way, in case you want to install it on your own laptop. It's available in the Debian repository, so you can do sudo apt-get install Gpaw. And it has packages for Fedora and Conda, I think. So quite a few distribution options. So also Golapalli asks whether one should create a separate Conda environment and install in order to solve some issues. But I'm afraid I don't really know anything about Conda. I'm not the one who maintains the Conda distribution for Gpaw, so I can't really answer that question, I'm sorry. So DP Rai has a question: how to cleave a surface from a bulk structure using ASE. So this depends a little bit on what you want to do. So one can build a structure a bulk structure and repeat it quite a few times, then you have a large block. And then you can delete parts of that block in order to take out a surface. There are also various different surface building tools in ASE. So if you would like to elaborate on the question, Rai, you are welcome to do that. Otherwise, I will just show. So in ASE, there is a significant amount of documentation. So for building surfaces, there is the ASE build module, which has all these shortcuts for common cases. So it's very common that you want a standard bulk structure, or that you want a molecule, or so there is a function for generating molecules from the G2 dataset. So standard small molecules, nothing very advanced. Then there are all these special cases of surfaces like the FCC 111, FCC 110, FCC 100, BCC, and some more specialized surfaces. Then there is a general surface building tool. Now let me see if I can find that. General crystal structures and surfaces. This is about crystal structures. Okay, I cannot remember where to find this in the documentation, and because of the okay, let's go to the ASE source because I happen to know that better. So here we have a general surface building tool. You can also find it if you search for the right name on the web page. So this tool allows generating a surface from a general lattice and Miller indices. So you can give it a primitive cell as an input, and Miller indices, and it does all the hard work. So this function can be used to generate a surface, and there will be examples also on the web page. Now, yes, there will be an ASR demo. So there is right after the break, which will be in a short time, there will be an ASR demo. So Shuo Xiao asks how the workflow adjusts core and memory distribution on supercomputers when it performs high throughput calculations. Now, in a short while, I'm going to start talking about ASR. So I guess I might as well answer that question now. When you start a calculation, it will use Gpaw's default parallelization. So it is actually Gpaw which chooses a parallelization depending on how many cores are available. This can be customized by looking up the parallelization options for Gpaw and making a choice. So typically, what Gpaw will actually do automatically is to parallelize as much as possible over k points, except if if that would lead to significant load distribution, in which case it makes a compromise where it also uses domain decomposition. And domain decomposition means that, so usually when we use Gpaw with ASR, we use the plane wave mode, and domain decomposition means that different groups of plane waves will be located on different cores. So it will, in practice, probably use a combination of k-point parallelization and parallelization over plane waves. Now, the question is, okay, so this was a question. So in order to actually allocate cores, this is a higher level task. So this would be controlled by the supercomputer's queuing software, often Slurm. Now, ASR is typically used together with MyQ for high throughput tasks. And MyQ is a front end for Slurm. So when setting it up, one specifies in a configuration file which kinds of core are available. And then one generates a workflow file. We will look more closely at that in the in a few days during the follow-up demonstration. So the workflow file specifies which cores it should run on and how many resources should be allocated to a job. So ASR does not itself choose the parallelization. It was between, in practice, MyQ and what the user tells Gpaw to do. So NOMAD asks, can we, did I forget somebody? NOMAD asks, can we add a new molecule to the G2 list? So the G2 list is basically a little database. And if you want, you can create your own database, but it won't be the G2. So one cannot add something to the G2 because it's already well defined in the code that it is exactly this set of molecules. But you can create a new database out of the G2 and add anything you want to it. Then there is a question, can we generate structure orderings for a disordered structure with partial occupancies using ASE? I know that the Sif format, which supports partial occupancies, is supported by ASE as well. And ASE can represent partial occupancies in some way. But it is not implemented with very many features. Most of ASE is unaware of partial occupancies. I'm not completely sure outside of that how to, if something additional was desired for a response here. So if somebody wants to install Gpaw and there are any issues, you can also ask on the mailing list or on the matrix channel. So there is a matrix channel for ASE. Matrix is a chat, and we can see here, this is what the ASE chat looks like. And we can see also, if it loads, we should be able to see that there is a corresponding Gpaw channel, and there is also an ASR channel, and there is also a channel for MyQ. So really all of these things have this, we have these matrix chats, and you can come and ask questions. Also, if you go to the web page of any of those pieces of software, there will be a contact page, and that contact page will have the link to the chat and the mailing lists and any other resources. So feel free to drop by. Now, time is passing, so there will also be the ASE part, and let's take a 15 minutes break before we do that. Okay, so now let's say that we continue at 12:15. So probably, let's see. So the difference between ASE and Gpaw versus ASR is that ASE and Gpaw have existed for a long time and are kind of stable, whereas ASR is very bleeding edge. Changes are happening all the time, and we are working to generalize this framework that was originally a driver for this 2D database, C2DB, and make it more general. And this also means that tutorials are a little bit lacking right now. They have not been updated to the new system. Not everything works completely in the new system. And some things are likely to change again. And this makes it a little bit more difficult to have proper, well-established tutorials. So instead of referring to the web page, I have a few slides showing more or less how things are right now. And I will go through and show, like before, how to actually run the calculations, but it will be a little bit more limited in scope. Next time, there will be a more complete tutorial showing also the high throughput aspects and how to submit things. Whereas here we will just take it slowly and look at in how to run recipes individually. And these slides I will share afterwards, and they will show more or less what I'm doing. Yeah, I suppose we can share them somewhere on the web page. Anyway, the first thing that we should learn is how to run a basic recipe. So most recipes, the way that ASR works, the user presumably wants to do thousands of calculations. And these calculations need to be organized in some way. And typically, this means that you have a lot of different materials, and you might put them into different folders. These folders you then organize into some kind of tree. And so this tree holds the actual calculations. Now, if we are going to get started bit by bit, let's try to create a single material and do some calculations with that. And well, I have here a mostly empty directory, and let's do the simplest case that we all know, namely silicon. We are going to do some simple calculations with that. So the first step is to figure out which material you want to run with. And ASE has a number of tools to help build these systems. So the first thing we can do is to use the ASE build command. It has a help page. Help pages are your friend. So for a lot of this work, we use these different command line tools, and you will always want to issue this --help to see what actually, how to actually use the command. So just, I assume that the sound is okay and the sharing of the screen is okay and all of that. Otherwise, please say so. Right. So we can use this build command if we have consulted the help page to build some kind of structure. So let's ask for a silicon in a diamond structure, and we create a file structure.json with that system. And this file looks like this. And this is the kind of input that we usually use in ASR for, this is a bit nicer to look at, for the geometries. And we can also open it in the ASE GUI. And we can see that this is a standard cell with 2 silicon atoms in it. And so ASR can be used either from Python or from the command line. And if you want to do advanced things, you probably eventually want Python, because then you can script everything, and you will want that if you do something complex. But a lot of things can be done from the command line, and those are, they have exactly the same interface. Only one is Python and the other is command line. So let's see, I said that the help pages are our friends. So let's run the ASR command line tool and see what it has to say. So you will see there are different subcommands here. One is to inspect results that were already calculated. One is to work with databases. One is to initialize a repository. One is to see what recipes are available. And then there are some, this one has to do with setting parameters. This one visualizes results without building a database. And the last one here runs an actual recipe. Let's first see what recipes are available. So we get quite a long list, which is will be consistent with what Christian showed you already. So most of them have some descriptive string, although that's not always the case yet. Now let's choose one and run it. So there is one called structure info, get structural information of atomic structure. So let's say that we want this. Now, if we consult the help page again, well, one of the steps to get started is to initialize an ASR repository. This is where ASR does all of its caching and stuff like that. And the first thing that we have to do before we can run a recipe is to initialize it, otherwise there will be an error. So if we run an ASR init, now it has magically initialized a repository here in this folder. And so now we can issue commands like ASR run and then ASR.structureInfo. So actually, as I said, the help pages are our friend. So if we want the help page for ASE structure info, we need to issue --help. Now, the funny thing about ASR run, which is not so user-friendly maybe, but it has its reasons, is that it takes a single argument, which is the thing that it should be running. So in order to access the help page of ASE structure info, you actually have to put it in quotation marks like this, and then you get the help page for that. And it says here, it takes as an input an atomic structure, the default being structure.json. and that was why it worked when I just ran it here. So now we can see if we run ASR cache. So if we remember we could see what things ASR has already been doing by using the cache subcommand. If we run ASR cache, it will give us a number of options. We can, for example, list the number of records in a cache. So we ran a recipe just before, and it produced some kind of record. Here we can see what records are in front of us. So there is this one. We can also run this ASR results command, and it will output some kind of representation of the results that are in front of us. Now, the new way to work with the cache is this cache command, and this is a bit more ad hoc and tied to how things used to be. So since the C2DB was meant to be published on the web, most of the information that is available in the form of web panels. So at some point we will add other output formats, but this is basically the representation of a web panel. Now, in order to actually view this web panel properly, what we can do is to gather it, or all of the thousands of results that we have probably in front of us, into a database. And then we can run a kind of local web server, and we can view the results locally. Let's try to do that. So let me just check if there are any questions. Not right now. Okay. So in the help page, we saw that there was a database subcommand, and this is for working with databases. So after we do all of our computations, what we do is to gather the result into a database, and we do this by running from tree, and then this directory is where we have our tree. It's not really a tree because there is only one calculation in it, but nevertheless we can do this, and it said that it did something. Now, in fact, it produced a file called database.db. So that is an ASE database. We can use the ASE database tool to ask what's in it. So now ASE has this database tool. I should not neglect to mention that there is also a kind of help command. So ASE databases are versatile way to work with different kind of calculations. You can attach specific pieces of information to them and store them and query the database and stuff like that. And the ASCDB command is an interface to working with these databases. So it has a lot of options. And as I said, we could see here by running ASCDB on the file, it can tell us that there is a system, silicon in it with 2 atoms, periodic boundary conditions, and some other basic informations. Outside of that, it has some special keys associated with it. This is all of the stuff that ASR has been generating. So it has a point group and a space group and stuff like that. Now, now that we have the database, we can run a web server on that database locally in order to visualize the data. So ASE database, this is called the database app, and we run that on top of the file. This starts a browser looking on, this starts a server, which we can then access in a web browser. So it runs on the local computer. And here we are viewing the database that we just created. So it only contains silicon. And we only ran the structure info recipe. The structure info basically defines this web panel. It has some help text and it has basic pieces of information such as a space group number, and other things. We can also see that this it has the cell vectors and other information. And then other metadata can be found here in miscellaneous, which it always tabulates. Now, what we have done now is to run a recipe and gather things into a database and visualize those results in a browser. And this is basically what we always do right now. So let's try to do some actual calculations. So we suppose we still have this structured JSON file, and now we want to do an actual calculation. So something that we can calculate, the standard thing that we would calculate for silicon perhaps, is a well-known band structure. So we consult the list of recipes again, and we see that there is something called band structure. There is also something called band structure.calculate. Now, in order to calculate a band structure, we also need a ground state. There is something called GS, which calculates the ground state, and also something called GS:calculate. Now, in ASR, the recipes tend to consist of multiple steps, one of them being the main step, and the others being individual instructions that are carried out as part of that step, and they are cached individually. And so the reason why there are two here is that the calculate instruction is the one that performs the main computation, and the other one performs, well, it calls the computation and then it performs some post-processing. So we can run either, but we can, if we want to run the ground state, so we will consult the help page for ASR run, and then we are supposed to give it this command, which we put in quotation marks. So let's run now the ASR.ground state first, and let's look at the help for that. Now, it takes a calculator as an argument, so those must be those will be the arguments that it uses to call Gpaw, because this one extracts a lot of data from, well, this one has not been generalized to properly support other calculators yet. It has default parameters that pertain to Gpaw, and it will extract a lot of results that are specific to Gpaw. So these are, generally speaking, very well converged parameters. It has a cutoff of 800 eV. That's very much for a PW calculation, and it also has an extremely high density of K points. It says here K points density 12. That's a little bit more than what we can probably should be running on a laptop. So I'm going to specify some other parameters. So there is a special shortcut syntax that you would use to specify, please choose everything like this except what comes now. So I put 3 dots. That means please use everything that was specified here except what I changed now. So let's say K points, and I just want a very coarse K point sampling. So let's say 4 times 4 times 4. And then let's say mode, and we want plane wave mode. We don't want plane wave mode with 800 eV, we just want the standard one, which is quite fast. So now we have done a few changes. and this we can run. And I needed to clear the cache. I need to initialize a new cache in this directory, sorry, because it was using a cache from a super directory. Sorry about that. So now it actually runs the calculation. And we can see that the computer is somehow working. And now it produced this ground state calculation. If we want, we can try to run the results command, and it generates a graph for us and outputs some representation of the web panel. So this means that it did something, and we can run ASR cache ls and see that indeed it ran some kind of ground state calculation. It also did a few other things that it always does, like figuring out whether the material is magnetic and checking some other things. So now we have the ground state. We can also run this band structure. Let's try to check the help. So it takes this calculator string, which is the same as before. Let's try to run the band structure. And we just leave the same parameters. Then it should reuse the previous calculation. Then it takes a special dictionary called BS restart, which is, so what it will do when we run the band structure calculation is that it will read the ground state calculation that we already performed, or perform it, if it was not performed already. And then it will, from that, it will fix the density and it will set some other convergence criteria. And then we get the band structure from that. I think I don't need to change any of these, but it will normally use 400 K points. I think that's a little bit much. So I'm going to tell it, please use only 40 K points. It will be a little bit ugly, but then we don't have to wait so long. So now we run it. Oh, and there's no such band structure, I think. Endpoints, actually. It's called endpoints. So it tells us that it found a cached record for the ground state that was good. And so now it is presumably calculating the band structure. Now, something that we can do is to, meanwhile, we take a little look at, I mentioned that ASR has this cache. Now, we should not be messing with the cache because it's something that ASR manages. But just in case you're interested, it's hidden in this .asr folder. So if you have an ASR repository, the .asr folder, that's where all of the information goes. So it has a lot of metadata, all of it dumped to JSON, some kind of table of the records that exist, and then we have different folders with files for each of the recipes that we ran. If we run the tree command, we can see an overview of this. We can see that here are some files containing the main results and metadata that we extracted from the calculations. And then there are some GPW files. Those are binary files from Gpaw which contain the calculated data. And also we can get we can see the text output files that Gpaw generates. So all of these things are created and saved in this way. Okay, now it finished calculating. So we can do what we always do. We can try to, well, we can run with the results again and have a look at if it outputs anything extra. So now we get to see a band structure here. And so we have a very bad k-point sampling here. So so there are very few points, but we can see that it kind of resembles a band structure. I'm not going to go that much into detail, but we can probably recognize some of these features as resembling the silicon band structure. This is the brewing zone showing the band path that we are using. It also shows where the valence band and conduction band maximum and minimum is located in the brewing zone. I think it might be a little bit off because we had a very coarse k-point sampling. This will confuse it a little bit.
Might I ask a small question? So this is regarding this automatic stuff that is done. Apparently, there is a magnetic anisotropy field, and that is like, seems like anisotropy calculations are not trivial. And so what is this exactly? Or you might, I mean, for silicon it's not an issue because there is no magnetic moments. But what I was just curious. I mean, it's not really important for this tutorial, I guess. But yeah.
So if you go to the C2DB page, so then you will be able to see the results, all of the data calculated for these 2D materials, and this will include this magnetic anisotropy. Now, there was this funny issue today with EduRoam not letting me into DGU web pages. So I'm not sure I can actually show it right now. You have to do it in your own browser.
No, it's not like, I understand what the anisotropy is. Like, I just wondered why it's calculated, or you know, it couldn't be calculated in the ground state energy calculation. It's just
right.
It shows up because it will later be populated, I guess. Or like, I was just confused that it showed up.
Yeah. So by default, the ground state recipe calls the magnetic anisotropy. It could also choose not to do that. So when you do a ground state calculation, it will first assume that the system is spin polarized, and so it will actually perform a spin polarized calculation unless you tell it otherwise. Then it will check whether the result was actually spin polarized, and then it will write a little bit of metadata. So it didn't really need to do anything having to do with magnetism, but I guess for consistency, it actually generates this little mag state file saying it's non-magnetic, and the magnetic anisotropy file, which also doesn't say very much in this case. So if we had been doing magnetic materials, it would probably contain something more relevant. Now,
okay, thank you.
There are a few questions here, so let's just take them while we're here. So, is it possible to add existing data computed out of ASR into a database? Well, the ASE tool or the Python interface to it allows adding data, any data, to any ASE DB. So it's definitely possible. If you have some data lying around, you just need to run the right command, and then you can add that data to the database, and you can make queries using that data also. So yes. Then can users create recipes and add them to the CLI? So right now, for reasons having to do with data persistence, there is a limitation that things need to be inside the source code, otherwise you cannot load it. But we want to allow libraries of recipes that are not inside the ASE, ASR source code. In other words, users will be able to create recipes and add them to the command line interface. Next time, actually, in the since this event also has another day of tutorials, I will write a and demonstrate how to write a recipe and add it. Then there is a question of how to convert Sif into an ASR file. That's a good question. So usually when we do our high throughput computing, we would get the data from some kind of source which doesn't already use an ASE format, and that's frequently Sif. So how would we convert a Sif file to an ASR file? Well, the ASR file is actually a standard ASE file, and ASE has tools to convert. So we, if we consult our help page here for the ASE command line tool, there is a convert command. It should probably have been listed in alphabetic order or something, but it wasn't. Anyway, there is a convert command, and it allows converting between different file formats. So let us say that I have the JSON file here. Now let us say ASE convert structure.json example.sif. Now I just did the opposite thing. I generated a Sif file out of the JSON file. So that was easy. Then I can also say ASE convert example.sif into other structure.json, or trajectory file, or XYZ. All of these files can be generated, and then we can open them with the GUI and check that things are the way that they should be. So this convert tool is quite powerful. It also has these helpful extra options. You can specify a little piece of code that you want to execute every time it converts something, so that you can attach special information or do some other programmatic processing. Also, I should mention there is it's possible you can run ASE info to get info about ASE. So if you just run it without any arguments, it will list all of the libraries that it depends on and whether they're installed and which version. You can also ask it for --help, and you can get help about formats and calculators. So let's see what it has to say about formats. This is the list of formats that ASE can read and write. So, so the ABINIT input format has read support and write support, and it supports only a single image, like a single structure. The if we scroll down and look at Sif, we can see that it has read support and write support. It supports multiple images, and then for some reason it's considered a binary format. That's because Sif is actually encoded into ISO, one of these ISO encodings, which is not Unicode, and therefore we consider it a binary. Don't mind that. So take a look at the formats listing, and because there are really a lot of format readers and writers, they can probably solve most problems. So thanks for the answer. Looking forward to the demo tomorrow. So the demo is not tomorrow. It is in a few weeks. There is a tomorrow. It is about fireworks, I think. Then Shasvi Ranawat asks whether web panels will be introduced in ASE DB. ASE already has a way to generate a generic web representation of a database. So in a way, it already has web panels, but the web panels are not extremely advanced. I think most of the push for presenting results inside web panels will happen in ASR. So what ASE is itself can visualize on a web page like this is, I think, mostly just a list of key value pairs with some nice formatting. But I actually didn't check that in detail. So then Daniel Fritsch asks about what about version-specific input/output, e.g. in VASP? That is an excellent question. So I assume you mean ASE formats. And this really depends on the people who maintain the ASE format readers and writers, the extent to which it supports the most recent version of a code. Usually for the codes that have a lot of activity, such as VASP, there are people maintaining it and making sure that it works with common use cases. So Alexander Thyssen tends to maintain the VASP calculator and associated formats in ASE. So that's in very good shape. As for other calculators, this depends really a lot on whether anybody has used it these last 4 years. Maybe there just hasn't been a person who used that code with ASE, and it won't support the newest version anymore. There is actually a lot of ongoing work to improve the integration testing and software quality when it comes to supporting these calculators, so we can be sure that all of the errors are fixed. But it is a major problem that some of the calculators are proprietary, so we don't have the license necessary to run these tests in public. Now, it's getting a bit late, so I would like to show one more thing before we have to stop. Let's get one step closer to actually running a high throughput. It will not really be high throughput, but I have here a script which the next step is with respect to what we already did. So what we did was to do a single calculation and visualize that. Well, what we want now is to do multiple calculations at the same time. Not with like advanced queuing systems or anything like that, just how would we do it in a basic way. So I have written this line of code which it imports from ASE this bulk function which knows the standard bulk systems for transition metals and some other elements. And then we write that into an ASE database. And let's see. So we have I have generated this little database now with a few bulk systems in it. And so let's pretend that this is a database with like 10,000 elements in it, and we want to get started on something high throughput. So this means that we would create our tree of calculation directories. So to this end, we would run ASR Database, and let's check the -- help page again, because we cannot probably remember this. So there is one here called main, which says unpack database into directory tree. And this will do what we want. Let's so here we have the database, and now we want our tree of computation directories. So we see ASR database main, and I guess we should ask it for help also. So it takes a database as an input, and so if we just run this, okay, so there is some kind of version issue. Let's just check. Sorry, these things change a lot, so so it can be a bit tricky sometimes. Okay. Right. Yeah. So there was a small issue with the compatibility of the software, which I hadn't corrected completely. So sorry about that. This command will do it. So what we did was to ask it to unpack the database into a tree with the following tree structure. So we name it tree / and then it has some magic codes that we can use to choose how it organizes things into directories. So if we run ls now, it has created this directory called tree, and inside of that, it has unpacked each element of the database according to its chemical formula. There are several ways to name these, and so one can also include space group and other things. This is helpful if you really have a lot of structures, because then you don't get like a single folder with a billion files in it. It becomes a bit more orderly. Then I specified to it that it should create a file called structured.json, which is a standard name. So we can see inside these, it has unpacked the structure into structured.json in each case. So now this should be reasonably good. We can now run our band structure example again. Let's try to do that. Band structure. So I will just insert some not too expensive parameters again. And then endpoints, not too many. And then we want to run it on multiple folders now. So we write this glob pattern, and let's see if that works. Actually, let's run it in parallel. And let's do a fresh cache before we start this. Okay, so now we have an empty cache in front of us. And then if we do --help, we can see that it tells us we can specify a number of jobs, so it does things in parallel. We ask for 4 because we have 4 calculations, just so it will be a little bit faster, since it's already 1 now and we're supposed to be ending. So now, hopefully it's calculating. We can see that there are 4 processes running. Now, if we had set things up using MyQ, we could have been submitting them and then also running each of them with MPI and a lot of processes. But again, this is just a simple demonstration on a laptop. So it's still running calculate. Let's see if there are any questions meanwhile. So how to choose whether I should use ASR or ASE or ASR database? I guess they can talk to each other. Yes. So an ASR database is an ASE database, but ASR adds extra stuff to it. So there isn't really any difference between them. The actual database software is called by ASE, or ASE implements code to do database queries and stuff like that. What ASR controls is rather which data goes into it, which key value pairs, which things can be queried and so on. And okay, so here we have another problem with the current version. I think I need to actually, in order to avoid these errors, I think I still need to do an init in each of these instead of initializing the main directory. Sorry about that. This is a bug. It will be fixed. It's, as I said, it's very bleeding edge and things are changing all of the time. But hopefully there will be a stable version very soon, and we shouldn't have this these crashes. Now we can see that inside each of the computation directories, it has created this .asr folder, and inside of that it has been organizing some files. Some of it has already been done. should be almost done now, I think. The last one is still computing. Okay, now it's done. So now we have our tree with results in it. We can do ASE database --help. Then we remember that the command is from tree, and then we ask for everything inside that tree. So this was collected now to a database. So we can see it has the same materials as before, but now it has all these keys that ASR has added. So ASCDB could talk to it. The original database that we had used, it did not have all this extra data. Now that we have gathered the results into a database, we can do ASR database app, and we start the web server on this database, and we can open it in a browser. And we can see that it has 4 rows. It has cobalt, copper, iron, nickel. So we can also do a search, and we can see that it finds the thing that we searched for. So on the C2DB, you can do much more advanced searches. I guess on a laptop, you would never have anything really worth searching for. So now I clicked it, and it has been generating these plots. So something is not quite right because we didn't add enough K points and stuff like that. So I think if we add more K points, it will get a more correct structure. Otherwise, it demagnetizes iron. That's a bit unphysical. But we can see that it generated some semblance of a band structure, and it will have the same data for the other materials. So this is how you run a, shall we say, low throughput calculation with ASR. And that concludes this first part of the tutorials. And next time we will look more at how to define workflows that can be submitted on a supercomputer. And yes, that would be it for today. So thank you very much. Are there any questions?
Is there tab completion, or will it be implemented?
I want to add tab completion. So the tools in ASC have tab completion. In ASR, they don't yet have tab completion. But the to-do list is very long, so it could take a little while. I guess you will be stuck with the --help pages for a while, or we will. Okay, I'm guessing that there are no more questions then. But I suppose I can hang around for a few minutes. Also, feel free to just unmute and ask questions. Okay, so So if I want to communicate with developers, the mailing list is the most usual way, right? The mailing list is fine. ASR doesn't have a mailing list, but ASR has a GitLab page in case there are issues, and also a matrix chat. So ASE and Gpaw have mailing lists. Those are pretty common for technical questions and general chit chat.
I have a question.
Mm-hmm.
Like I'm trying to install, I'm using Windows operating system. So I follow the documentation on the ASE page to install ASE. But
Mm-hmm.
he's saying that he said, warning, the scripts py.test.excel and py.test.excel are installed in the directory which is not on the path. So consider adding this directory to path. So I don't know what that something means, or if I can.
I'm not really familiar with Windows, but normally this would mean that so the system has a particular path, such that when you issue a command, it will look through that path or multiple paths to find them, and I guess you need to configure that. But how to do that in Windows, I don't know.
Okay, that's okay. Maybe I will. Okay, thank you.
Then I wonder if there are best practices recommendations for running workflows on HPC clusters. It's very different from running things locally. Well, so the one needs to set the parameters, and that would work in the same way. But on an HPC cluster, the difference is that when we start the computations, we would generally do it with MyQ, which then submits a job through Slurm or Talk. And then MyQ will keep track of the running jobs. And MyQ can also have specifications for, so let's say that one job runs out of memory. Then if you suspect that your database is a little bit uneven and some of them might run out of memory, well, then you tell it that, okay, if something fails with a memory error, just resubmit it with more memory. So there is this layer of giving instructions to the HPC system, which comes on top of what we have already seen. Other than that, I don't think it is too different. You would use the same commands basically to collect a database of the calculated results. And also there is a question of definition of workflows, so that resources are divided somehow between different kinds of computation. But that falls more under the HPC configuration, I guess. Okay, so I think that was all then. So thank you, everyone.
Thank you.
See you next time.
Thank you.